Okay, I'm talking about information theory, fitness as in evaluating programs, and sampling how the programs work. My name is John Woodward, and I'm from the University of Stirling. This is joint work with Colin who's down here, from the University of Kent, who's speaking next. So there's a bit of overlap here. Okay, so here's an outline of the talk. I'll just say a few words about common goal complexity before we start. Then I'll talk about how we can use this in testing. This is just a simple start, so it's very rudimentary work. But we can start using common goal complexity in this work. I've actually just deleted the slides on Occam's razor. I think this is a very interesting piece of work, but I haven't got time to talk about it. And then this is the main part of the talk here. So we're going to be using information distance to measure the progress of incomplete programs, so programs that are still in development. And we're going to compare two measures. We're going to compare a pixel measure against a picture distance. And this is a measure we normally use when looking at programs, counting how many test cases they passed. And this is a measure we're going to use which is based on common goal complexity. And the analogy I like to use is if you're in a maths exam and you hand your maths homework to the teacher, this is a bit like saying, is the answer right or wrong? This is a bit like saying, how good is the working? So the student might be very clever and get to the very end of the computation, but they make a mistake in the last part because they're nervous in the exam. But actually, they're a better mathematician. So this is a better measure of mathematic ability. And then, as David said, this is sort of work based on genetic programming, and we're going to compare our method with genetic programming. Just out of interest, how many of you know genetic programming? Okay, about half, so I've got one slide just quickly going over that. Okay, so let me just introduce genetic programming and then attack it. So I want to destroy genetic programming as well. So basically, genetic programming, you have a set of test cases and you want to synthesize a program that will match those test cases and satisfy it. So it's programming by example, if you like. And the idea is you use natural evolution, so you breed a population of computer programs. The good ones carry on, the bad ones die in repeat. And it's usually this idea of survival of the fittest, but the fittest is what measure are we using to measure the fitness? This is a biologically inspired process, but just because evolution is good at searching the space of DNA, does that imply it's good at searching the space of computer programs? Not at all. This process also relies heavily on randomness. And here I mean randomness is in probability, not Kolmogorov randomness. They're two different things. They're two completely different things. So this is here you might generate a set of programs initially at random, and during the process you're going to change the programs at random, and you select which programs go on to the next generation at random. Sorry, with a bit of randomness, it's not completely random. But in your typical genetic algorithm or genetic programming algorithm, there's a lot of randomness. And randomness just means we don't know what we're doing. So let's replace that with some information theory. Well, let's try and start to replace that with some information theory. So this is a bit of an overlap with David's talk, but it's got pictures of the guys. So this is Kolmogorov. He was a much more established mathematician at the time, which is why it took his name. He was the guy who invented it, Solomonov. I met him a few years ago, actually, at a conference. And I was the only person to ask a question in the question and answer session at the end. He called me a cheeky postdoc. He had his 85th birthday a few years ago, and he had a conference, so I got a paper in there. It was in Australia, and I missed my bloody plane. Okay. So here are 3-bit strings. This one here is all zeros. If you were asked to communicate this with somebody, you just say repeat 60 times 0. This contains the same information as this. They're equivalent. This one here, 001, 001, 001. Same pattern, repeat this time 20 times 001. This one here, no pattern. You just have to say the whole thing. On average, the number of zeros and ones here is about 50-50. Here it's a third, so this is telling you straight away it's compressible. This one's got no ones in, so it's highly compressible. Okay, David said a few words of these, but The Komogorov complexity is the length of the shortest program that prints that bit string and halts. So that's a standard definition you'll probably hear a few times today. One way we can get at it is by looking at how compressible the bit string is. So it's an upper bound on the complexity. It's independent of the machine you run it on or the programming language. And Komogorov complexity is a generalization of channel entropy because it does away with probability distributions. In channel entropy, each bit is assumed to be independent. In Komogorov complexity, you can let go of that. Okay, so here's the famous invariance theorem. I started life as a theoretical physicist, so whenever I hear the word invariance, the hairs on the back of my neck go up because it's important. So the complexity of some object x, a bit string x, with reference to language 1, is bounded above by the complexity in language 2, plus, if you like, the dictionary to convert between the two languages. So this is converting from language 1 to language 2. So it's an emulator, you can emulate one computer language with another. So obviously we can write this down here as well. It's the same equation, just switching the 1s and 2s. And we can put them together in one equation here and sandwich them. So the upper bound of the complexity is given by C21, and the lower bound is C12. If you want a little soundbite to remember that, it's like the complexity of the works of Shakespeare in English is going to be less than the complexity in, say, French, but you need an English-French dictionary. And the complexity below is the complexity in French minus the complexity of the English-French dictionary, so it's the other way around. It's not symmetric. These two can be and often are different. Okay, so we're going to talk about testing for a minute or two. So all I'm going to do is say, in genetic programming you have a set of test cases, and normally you just test your program against all the test cases. That's fine, but it's expensive. So can we do something a bit clever and just start feeding in test cases one by one? So if we've got a program which passes all the test cases, can we start adding new test cases just incrementally? So a few definitions. We can talk about the size of a program. You can take any definition of size you want, it doesn't matter. Number of lines or number of bits. The complexity of a program is the size of the smallest program with the same functionality. So you can always add bits to a program, but how much can you take away before you lose functionality? We can also talk about the complexity of a set of test cases, which is the same definition. What's the complexity of the program that you need to meet that set of test cases? So we can start writing some theorems down. To me, theorems are a start. A lot of this biologically inspired stuff is all right, but I'll stand out of view of the camera there in case Bill Langdon's listening. Biologically inspired is all right to a certain extent, but when it breaks down, what do you do next? If you've got theory behind you, you can keep making steps in the right direction. So imagine you've got two sets of test cases, a set U and a set V. If the set U is a subset of the test V, then the complexity of U is less than the complexity of V. I think that's quite straightforward. If the number of test cases in U is less than the number of test cases in V, this doesn't follow. But we can still say the expected complexity is less. Okay, I think those are quite intuitive if you sit down and think about them for a while. If not, we can talk in the break. Okay, so I don't want to go into too many details of the algorithm here, but all I'm going to say is we're going to generate a program, and if it passes a test case, we're going to give it another, good boy, have another test case. And we're going to keep feeding in test cases. So after we've had a program which has passed one test case, we're going to say, can you now solve the problem? And if you've only passed one test case out of 16, I think, in total, usually you can't, because you haven't seen enough information yet. But at around 8 test cases here, most programs, once they've seen that, so once they've seen 8 test cases, they can solve all test cases. Okay, so this is, if you like, it's the Komogorov complexity of the problem. Or an estimate of the Komogorov complexity. Some programs, they might solve 14 out of 16 test cases, and you say, can you go on to solve the remaining test cases? Some of them can, some of them can't.
What do you mean by solve?
Satisfy.
Satisfy.
Sorry, yeah. Sorry, I'm from a machine learning background, so I keep...
Right. And these tests are randomly sampled from input domain?
Yeah, right. From where, sorry?
These tests you use are randomly sampled from input domain?
Not infinite, no, it's a this is a finite domain, it's just Boolean.
Okay.
I'll skip that slide because of time, but so we can ask if you've got a program which passes a certain number of test cases, how many more test cases can I give it before it fails? So most of them, you just give it one more test case and it fails. So it's only known to satisfy the test cases you've given it. Occasionally you're lucky and it might get 2 or 3 test cases and then fails. Okay. But you can see this definite curve here. So a program doesn't suddenly just learn a test case, it's going through incremental changes. Okay, that should be half time. So that was just a brief investigation of using Kolmogorov complexity to examine test cases. What I want to do now is talk about using Kolmogorov complexity as a measure of how good programs are as we're constructing them.
Where does the test cases come from, and what is the oracle?
It's a lookup table. The oracle is just a lookup table. It was even parity.
And is it random sample of the input space?
Sorry?
Is it random sample, or are these existing test cases?
They're existing test cases. So there are 16 test cases, and I keep them in a pot, and I just feed them across one by one without replacement. So we need to be able to measure things. That's quite an obvious statement, but often we measure complete programs. So here's a complete program. How well does it perform? How can we measure incomplete programs? So one thing we can look at is this question here, number 2, is how many instructions do we need to complete the program? So I've half written my program, or I've written some of it. How many more instructions do I need to complete it? So in other words, whatever the Kolmogorov complexities of the program I've written, what is the Kolmogorov complexity of the test case? We're looking at the gap. How much do I need to fill in? This should come clear enough in the next few slides. So this is the conventional view, is how many test cases have we passed? Each test case you pass or fail. What we want to measure is the number of instructions needed to complete the writing of the program. I think conceptually that's quite straightforward. How we do that is a bit more difficult.
But it's assuming that the part of the program is correct. That you know that part of the program is correct. That you have the notion of correctness.
Can I pause that question? So imagine this is a binary string indicating your test cases on the program that you want. Imagine this program here, and it's actually wrong on every test case. So when you wanted a 0, it's given a 1, and vice versa. So if you count test cases passed in the conventional sense, it's the worst possible scenario. But this program is easy to repair because all you need to do is invert the output, and then we've got a completely correct program. Here's another program here, which is actually better in terms of the number of test cases it passes. But if you ask me, how do I complete this program to satisfy these test cases, I don't know. So I think these next 2 pictures are the most important part of this talk. So imagine this is our target picture over here. And your computer has generated this picture here. If we look at each pixel, pixel by pixel, what score can we give it? Well, imagine there are n pixels here. It's black, black, black. Over here it's white, white, white. So it's wrong, wrong, wrong. And then white, 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 black, 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 wrong, wrong, wrong. So this distance here is going to be n. It's got everything wrong. Here's a blank picture. I picked this picture here because it's symmetrical, half black, half white. So this distance here is n over 2. That's if we count pixels. Let's do something different and count the number of instructions to convert one picture into another. So if I gave you a black square or rectangle and said convert that into that, you could do that with one instruction or one line. Just iterate over the image and invert every bit. If I gave you this image here and I said I didn't want that, I want the negative of it, you could say iterate over the image, invert every bit. Yeah? Okay, let me ask you a question. What's this distance here? So this distance here is, if you like, 1 unit of computation. What's this distance here? Let me ask you a simpler question then.
Quite a big distance, I would say.
Sorry?
That distance there is the complexity of the image.
Yes. The complexity of this is 0 or 1, there's not much information in there. But to get to this image here, there's no information there that's useful. So this distance here is the Komogora complexity of this image. Yeah. Look at those two pictures again. That's what we're doing when we measure test cases. That's what we're doing when we measure how much computation we need to do. There's an analogy here with building arch bridges, but I'm running out of time, so I'll come back to that in the questions if you're interested.
Are you running out of time? I'm not. I think I took up the whole of your talk time.
Yeah, I know, but I couldn't finish there.
We'll just move everybody.
Okay. I've got 3 minutes left according to this, but if you're happy with me going over it.
Well, I think it's got till 12:20, so
Okay.
you can relax a bit.
Okay. So let me just, this analogy isn't 100%, but I think it's quite nice. Imagine you're building an arch bridge here. Each of these stones rests on its neighbour. Yeah? The way these bridges are built is they don't put the bricks here one by one. You can't just build a half bridge and go home and have lunch and come back again. What they do is they build a wooden support, then they put the bricks on one by one, and then they actually burn the wooden support away. Yeah, that's a bit like a computer program. If a couple of these instructions are missing, you haven't finished your job. You need to get all of the instructions. So it's a bit like taking a computer program and executing it from start to end and only being able to evaluate it once you've finished. Yeah, you can only march your soldiers across here once the bridge is complete. What we'd like to do is build half of the program, go home and have lunch. We could even test it. We could march our soldiers halfway across and back again. Yeah. So what we'd like to be able to do is say, well, here's the program we'd like to write, but we've only got to here. Can we evaluate this part of the program? And all I'm saying is, this distance here is the Komogora complexity of the test cases. This is the complexity of the program you've written so far, and the difference is how much work we need to do. So the proposition is, can we use things like entropy and information theory and algorithmic complexity to assign fitness to programs better than just counting test cases passed? And the way we're going to do this is by sampling the semantic vectors. So we look at the program on different test cases and see what information they've processed at that point. I'll explain that in another slide in a minute. Okay, so imagine this is our input vector, so it's a 4-bit input problem, and our target function is just parity, I think even or odd parity. Okay, so it's just counting the number of bits. If the number of bits is even, 0, 0, 0, 0, 4, return 1. So here we generate a program. It's V0 XOR V1. Okay. If you were doing GP, you'd say, well, here's my complete program. How many test cases does it pass? We're not doing that. We're saying, here's a bit of a program. How much more work do we need to do to evaluate it? Sorry, to get to where we want to be. Here's another program, V0 and V1. And there's the output vector. So out of those two, which program is better? So what we can do here is we can calculate the Hamming distance, the difference between F1 and where we want to be going. So this is the difference between F1 and where we want to be, and this is the difference between F2 and where we want to be. And if we look at this, we can estimate the Komogora complexity and say, well, look, actually 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. That's highly compressible. This is not as compressible. Therefore, F1 is a better function than F2.
John, but the compressibility just comes from the order of the input.
Yes. Can you say that question as well? So you mean the order of the input?
Yeah, I mean,
Yes, you're completely right.
if you take a random order, then you have a random compressibility.
Yeah. Okay, so there are actually two issues here. One is that we're going to order. We need some order. That's the first thing.
Why do we need an order over the inputs?
Because what you just said. If I put these in a random order, I can make this one more compressible than this one. So the order is important.
So what is the measure of the quality?
Yeah.
And what is best?
Yeah.
What does best mean?
So okay, you need ordered test cases.
What you mean is you need to, shall we say, can't think of the word.
What's the difference?
You need to just fix an order.
Yeah, you
and stick
need
to
to be
it.
consistent. That's it.
Is that what you're saying?
No, more than that. You need to be. I think we need to be more than that, don't we, Colin? We need.
Fixing an order is a good start, I think. Yeah, I think that's
Yeah, it's a start, but the question is there an intrinsic ordering that you can make use of?
We've just gone for lexicographical at the moment.
Lexicographical, okay.
Yeah.
That's kind of intrinsic.
Yeah.
So I understand it like you need the order to get the compressibility,
Yes.
but there's no requirement other than that that we need an order of the inputs.
Yeah. Yeah.
So no prioritization, nothing.
No.
So basically, the order one chooses will have a strong impact on the choice of what is more compressible.
Yes.
So if I change the order of the input, I will get F2 as more
You could
compressible.
change. Yeah. If you change the order of input, this could change. Yeah.
And how do you know it's not just arbitrary then?
Well, this is the natural ordering. Yeah.
Ooh, cheeky,
Well, there's a bigger problem.
I'm
Okay.
sure.
Can I?
Yeah.
I think one possibility is you introduce another algorithm for ordering. So measure the complexity for the algorithm for ordering.
Oh yeah, that's clever. Yeah.
Right.
We've got some ideas around how we can overcome this, but this is just the first swipe at it. So I completely take on board what you're saying, and I agree. I agree. So I'd say the next slide is the least important in the talk, and it's actually the algorithm. But I don't want you to sort of think, well, this is the algorithm they're proposing. It's not one of these talks where we say, here's an algorithm, this is what we're doing. All we're doing in this algorithm is generating a set of instructions at the beginning and seeing which ones are easier to extend to minimise the measure of distance, information distance. So all we're doing there is we're generating these initial programs like this F1 and F2 or F2 X 0 X3, that kind of thing. Then we're going to measure the Hamming distance between the outputs they produce and the outputs we want in the test cases, and then we're going to decide which ones are better by looking at the compression distance between them. Okay, so we're not counting test cases. Okay, so in example run we might generate some programs here. This is the compressed distance between their bit string and the target bit string.
Can I have another question? That
Yeah.
relates back to that one. So with that switch of the slide, you abandoned your order of inputs, right? It does not any longer appear there. Now you're measuring the Hamming difference between the output for one test case and the expected output, right?
Not for one test, but across test cases.
Yeah, so are you concatenating all the outputs and comparing that to all the...
Yes, yes. So we've got 16 inputs. So we've got 16 output cases.
Yeah.
Each subprogram will produce 16 output cases. We're taking the difference between them and then saying is that...
Between the concatenation of all 16, because you have an order, or between each test expected output and observed output?
The second one, we're taking the difference between them. We're not concatenating anything.
Okay, so there's no relation between that slide and the following slide. Because you no longer have an order of the input.
The order of the input is kind of implicit. We're just fixing that at the beginning of the program. We're not changing the order of the input.
Yeah, but here the order of the input doesn't really matter. Because if you change the input order, you're getting the same result in this.
If we change the input order, things go wrong. We're not touching the input order. I don't think I'm answering your question, but
Okay, if you're changing the input order, why are
We're not
things going wrong? That was the argument.
okay. Let me say this a different way. Do you agree this string is more compressible than this one?
Without any kind of context, I would have computed. I mean,
Exactly. Computed.
Yes.
Yeah.
Yes.
I was going to say if you don't.
yeah. Okay.
But if I switch the order of the test cases, I could make this all half zeros and half ones
Yes,
here.
yeah, I understand that slide.
Okay.
The question is,
Yeah.
here you are relying on basically the order of the test cases.
Yeah.
And the next slide, you no longer have an order of the test
No,
cases.
it's implicit, yes.
We're not.
Yeah, but I mean, you just argued that you are not concatenating the outputs any longer, and before it was a concatenation of the outputs.
It was never a concatenation.
Well, the previous slide is a concatenation.
It's a difference.
You
That
have
can
No,
just
you
that
can't
way.
say-
Yeah.
That way, not that
Politically,
way.
it's a
you have 16
concatenation.
different
Yeah. Okay.
inputs.
Yeah.
And you have an output of one single bit, and you're concatenating all bits there. And in the other one, you haven't given the number of inputs, and you're measuring the distance between every output for every input. And if you change, and you don't do concatenation of the outputs overall to get you this right?
Colin, I don't find
I think the problem here is that Jens is that you're assuming something which, and Jens is sort of asking, are you assuming it? Because it's not explicit in your algorithm. So, and the assumption is that when you're talking about outputs and so on, you're actually talking about what Jens calls the concatenation of the outputs.
An
In
ordered
other
set-
words,
an
the
ordered
outputs
set
in
of-
order of the inputs.
And yes, that's correct. Yes.
And that is there.
That
It's
is there,
explicit.
yeah.
But sorry, implicit.
Implicit, yeah.
But it's not explicit in the algorithm.
So you are actually concatenating the outputs.
Yes.
Yes.
And not doing the difference between every individual expected output compared to the actual output.
So the first one.
The first one, you're concatenating.
Yes.
Because you previously said something different.
A difference first, then concatenation.
What diff? No.
No, concatenation first.
Yeah.
So we took
One.
the first test case. Yeah.
Yeah.
And this function here is 0. Okay, the one we want is 1. You can do it either way. I'm running this function here on all test cases, concatenating them if you, yeah? Then I'm taking the difference and concatenating all the differences.
Yeah. Okay.
And then compressing that.
Yes.
So we can do the difference and concatenate, or concatenate and then take the difference.
Okay.
I
Yeah.
think that's where the
Yeah.
confusion is.
Okay. Now it makes clear that the concatenation is over the difference of the output.
So,
Yes.
yeah, I didn't think it was going to be that complicated.
It wasn't. But
Okay.
you've run out of time for the talk now. But since Jens has been biting heavily into your talk, can you give us another 5 minutes and then we'll
Yeah, sure.
ask some more questions?
So let me just say, if this was all zeros, the compression of that bit string is 23 with G's, I think it was.
Yeah.
So we can start to generate little programs and just say, how good are you at a step towards solving this problem? So here's a couple that are generated, and their values are here. And they're all just a little bit above 23. So after one round of saying, what's the next instruction, we get something like this. Then we say, what's the next instruction after that? And the compression distance goes down, so we've got a slightly more complicated program. And all we're doing is asking, what's the next best instruction we can add? Okay. If you think about it, it's if you're using Commodore Complex as a guide, the space is unimodal. Okay. The solution we've got here is a perfect solution. We found, so it's got this value 23 here, which corresponds to 16 zeros. That's the answer. We've still got a bit of stochasticity in this algorithm, which I think we can get rid of actually. I don't know why we've got that actually now, thinking about it. We can rerun it again. Again, after just 4 iterations to get a perfect solution. If you use your standard genetic programming algorithm where you breed a population of programs, let them all do crossover, pick the best based on the number of test cases, mutate them, blah, 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 you get garbage. I shouldn't say garbage. You get stuff like that. Okay, it's solved test cases, but would you rather have that or that? Okay, 2 more slides and then I'll shut up. Genetic programming is measuring the wrong thing. The number of test cases is good when you say, here's my final program, how good is it? My final piece of software wants the minimum number of test cases to fail. But during development, what I want to know is, how many more instructions do I need to complete the program? And that's basically Kolmogorov. So what we've got here is a way of evaluating not programs, but parts of programs which are going to later become parts of the complete solution. Okay. What we're trying to do is move away from this bio-inspired stuff. There's lots of holes in this work. Again, so I completely hold my hand with this. There's lots of holes in this work. But if you're from the bio-inspired community and you're working with, say, neural networks, their answer will be, well, let's make it more like the brain. But is that going to guarantee that it's going to work? No. If you've got a proper founding in information theory, and it doesn't work, there's still a few things we can do to get in the right direction. So we're on the right footing, I think. I know Colin and I, we met at a cow actually. It was a genetic programming cow about a year ago, and we started these conversations. And every time we come up against the wall and think, no, it's not working, we've got past it, so it keeps going. Okay, so final thought. What we mean by a better program during development is how much regularity is there between its outputs and the outputs we want to get. By regularity, I mean Kolmogorov complexity or compression distance. Once the final program is finally released, then we care about the number of test cases it passes. But these are 2 different things. So my thought I want to leave you with, if you like, is I come from a theoretical physics background. Energy is important in theoretical physics. It drives physics. So surely information theory should be as central to software engineering as energy is to physics. And I think if we have proper metrics, we're going to make programming more of a science than an art. Okay, so that's it. I think it's going to be, well, maybe I should hand straight over to Colin and let him dig me out of the hole.
Thank you.